Beneath every modern construction site lies an invisible web of high-energy power. Unlike a moving crane, electrical hazards offer no visual warning. Electricity is a silent force that actively seeks the path of least resistance to Earth, and if a worker is in that path, their body becomes the conductor. In construction health and safety, effective protection is built through a structural hierarchy. First, absolute isolation. Second, voltage reduction. And third, physical exclusion. To understand this architecture, we will build it from the ground up. We will look at the physics of a lethal shock, analyze the hardware designed to step down that energy, and map out the strict site-wide controls for excavations and overhead lines. From an examiner's perspective, electricity is a planning and isolation challenge. Success depends on proving you can keep human beings completely separated from live energy. Construction environments change daily as steel structures grow and trenches deepen. This constant variation means electrical controls must be systematically engineered into every stage of the site's daily operations. Managing hazards requires an environment where human contact with live energy is physically and administratively impossible. This equation shows Ohm's law. It states that voltage equals current multiplied by resistance. On a construction site, this is the exact mathematical formula for human injury. Current, measured in amps, is the actual killing mechanism. If a current reaches between 80 and 100 milliamps across the heart, it triggers ventricular fibrillation and cardiac arrest. The human body provides resistance. However, that resistance is highly variable. When a worker is exposed to rain, sweat, or wet site conditions, their electrical resistance drops significantly. With resistance dropping in wet conditions, the math offers only one solution. To prevent the current from reaching that fatal 80 milliamp threshold, site planners must drastically lower the voltage. Even at lower currents, electricity presents severe secondary hazards. At just 15 milliamps, alternating current causes involuntary muscular contraction. This results in a let-go failure. The worker cannot release the live tool, prolonging the shock and frequently causing secondary falls from ladders. Because site conditions inevitably reduce human electrical resistance, managers must alter the electrical system itself rather than relying on individual resilience. There is a common assumption that standard electrical fuses are designed to save human lives. A fuse is strictly an overcurrent protection device. It contains a wire that melts to break the circuit, but it acts too slowly to stop a fatal shock. Its purpose is to prevent equipment from melting and to stop electrical fires. This is a 110-volt center tap to earth, or CTE, transformer. This is the primary hardware mitigation required for portable tools on UK construction sites. The CTE system splits the 110-volt supply. Under fault conditions, the maximum shock voltage delivered to the worker is halved to 55 volts, which keeps the current below the fatal threshold. To actively protect human life from shock, sites use a residual current device, or RCD. The RCD acts as a precise scale. It continuously monitors the circuit to ensure the current leaving on the live wire exactly matches the current returning on the neutral wire. If the RCD detects a discrepancy, meaning current is leaking into the earth, perhaps through a worker, it reacts instantly. A leak of just 30 milliamps will cause the device to break the circuit in 30 milliseconds. Class 2 equipment provides further protection. Known as double insulation, this equipment features a secondary, non-conductive plastic barrier inside the casing, ensuring no live internal parts can touch the outer shell. Maintaining this hardware involves two distinct steps. Workers perform daily visual checks for damaged cables. Separately, trained personnel conduct portable appliance testing, or PAT, to provide a formal, documented record of electrical integrity. While 110-volt CTE systems and RCDs mitigate the physics of a strike, hardware eventually degrades. Complete safety requires foolproof administrative isolation. The administrative safe system of work is the protocol that prevents electrical energy from reaching the worker in the first place. UK law is specific. Live working is prohibited unless dead working is completely unreasonable and stringent precautions are established. The dead working algorithm follows a strict sequence. Step 1, identify the correct circuit. Step 2, isolate the power supply completely. Step 3 is securing the isolation. This requires locking off the breaker with a physical padlock to prevent anyone from inadvertently re-energizing the system. Step 4 is mandatory. Use specialized test equipment to physically prove the circuit is dead before anyone touches the conductors. The final physical step is applying earths to the system. This safely grounds any residual electrical charge or accidental power spikes. These isolation steps are documented and enforced via an electrical permit to work. The permit dictates sequence, PPE, and emergency procedures. It requires a physical signature from a competent, authorized manager who takes responsibility for the isolation. This permit functions as a final administrative lock, ensuring that the physical energy remains contained behind a wall of documented accountability. Electrical hazards also include catastrophic macro strikes involving heavy plant machinery and site topography. Overhead power lines introduce an extreme hazard due to a phenomenon known as electrical arcing. High-voltage energy can jump across physical air gaps to instantly energize the metal arm of a crane or an excavator without direct contact. Following GS6 guidelines, the primary control is pre-planning. Site managers must consult the service provider to either divert the lines or isolate the power before work begins. If lines remain live, strict spatial controls are mandatory. Sites must erect physical barriers at least 6 meters from the line and install height-restricting goalposts at crossing points. Beneath the surface lies the risk of striking buried underground power cables during site excavation. Before breaking ground, site managers secure utility plans and physically trace the area using a cable avoidance tool, or CAT scanner. Digging rules are exact. Excavators must dig alongside the marked service, never directly above it. Final exposure of the live cable is done by careful horizontal hand digging. Managing macro hazards requires a specific operational discipline, treating the air above and the ground below as fully live until spatial exclusion meticulously proves otherwise. This matrix synthesizes the 3 distinct layers of electrical safety: hardware, isolation, and topography. Hardware limits the physics of the shock. 110-volt CTE transformers and RCDs cap the voltage and break the circuit if accidental contact occurs. Isolation enforces the dead working algorithm through permits and lock-off protocols. Topography management involves utility plans, CAT scanners, and GS6 exclusion zones to handle hazards hidden in the ground and sky. Always prioritize absolute isolation and dead working protocols. These are the primary defenses against electrical injury. The electrical safety of a construction site is determined by the rigor of its preparation before work begins. Mastering electricity in construction means engineering a system where current is strictly bound and entirely separated from the worker.